So we start again, and it is my great honor to introduce our next speaker, Dr. Alfonso Nardi. He graduated cum laude in electronics engineering at Politecnico di Milano and got his PhD in photonics in 2023 at the Electrical Engineering Department of ETH Zurich. He currently holds a postdoctoral position at the Institute for Quantum Electronics of ETH in the Optical Nanomaterial Group. And now his research focuses on harnessing nonlinear optical processes in disordered materials. He has made significant contribution to the fields of nonlinear optics and random media and authored several scientific publications. Some of his notable works include encoding information in the mutual coherence of spatially separated light beams and controlling spatial coherence with an optical complex medium. Noteworthy is also his work on large-scale photonic computing with nonlinear disordered media. And now I will hand over to Dr. Alfonso Nardi for his presentation. Thank you so much.
Yeah, thank you very much. Thank you for the kind presentation. Thank you for inviting me and to be here to listen to the talk. I will move to, yeah. And the talk starts from here. It is the desk that everybody would like to have because it's clean, it's simple. We feel like we can work very well on this, but very fast what we end up with is something like that. And truth is, the reason why we end up with something like this is that this is much more efficient to work with. If you work with in a disordered environment, and you work it, of course, in a smart way, you organize it in a smart way, disorder can be much more efficient than a very ordered and nice space. And in photonics can be similar, okay? And this is what I try to convince you today. Today we also have Professor Sellame that will talk about integrated optics, I guess. And you can do beautiful stuff with integrated optics. You can do beautiful experiments. It's awesome what you can achieve. But for sure, it's something that it's difficult to fabricate. You have a fixed task. Okay, each integrated circuit do something very specific. It's expensive to fabricate and difficult to scale up. What I want to convince you today is that with disorder, okay, if we look at disorder from the right point of view, what we can achieve is something that it is, yes, complex, but it is simple to fabricate. It doesn't cost much. It has a lot of degrees of freedom to achieve different tools for optics with the same medium. So the outline is the following. We start from what complex media are, and at the beginning, what is a problem? Okay, it's a problem to solve most of the time, but what I want to focus on is why it can be a resource for photonics. And we go through different examples of this. And finally, two of the possible applications in computing in particular, one in quantum computing and one which is my expertise in photonic machine learning. So we start from what a complex medium is, and to this aim, we start to how in the optical nanomaterial group at ETH we do this, and we start from these very precisely done nanocubes, okay? They're polydispersed between 100 and 400 nanometers, and then, okay, we start from something that beautiful and we just bunch it together in a disordered structure, okay? And this is a way to achieve a disordered medium. But okay, you have to start from very beautifully designed nanocubes. We will see later why. But if you don't want to go from there, then you can just take a sunscreen and put it on your sample. This will be your disorder medium. If you don't want to do drop casting, too much of an effort, you can just get a sugar cube and we'll still do the job. Okay, these are all examples that I actually used in the lab during my research. And these are possible to use because a complex medium has two properties. One has to be wide, so it does not absorb, and it has to be opaque. These are the two properties, and of course, okay, the different complex media then serves for different purposes. To understand why this can be a problem, I will go through an example, okay? And the example is the following. We are in an apartment, okay? It's a two-room apartment, and it's completely white. It's a completely white room, so there's no absorption anywhere, okay? We sit in the chair, and we want to comfortably look at the rows. So what we have is that some light that goes to the rows, acquire the spatial information, and then what we expect is that if there is no absorption, then somehow the information should arrive to my eyes. Well, it turns out that it doesn't. I mean, we know that we just see a white wall, and the question is why? Why we don't see anything? And to answer this question, it's not that easy. Actually, we have to look inside the wall. And what happens is that the light that gets the information from the rows then gets scattered inside the wall and gets out completely scrambled. So we don't know anymore. Okay, we don't know anymore what was the initial information. This is why we cannot see the rows. But then let me tell you something. Okay, what we can do, and it's important for random media, they are random, but they are deterministic. So if we measure their effect, what we can do is to pre-compensate for the effect of the wall. And then we can use a modulator. Here is a special light modulator. We will talk about this later. To pre-compensate the effect of the wall and then retrieve the image of the rows afterwards. And this is actually, it looks like magic, but it's actually measurements. Okay, there was this paper very similar. The object is not a rose, it's a G, and the SLM is after the wall. But what you can do is without correction, without the SLM, you don't see anything. And with it, you retrieve the initial object. Okay, and yeah, we can enjoy our, our rows seated from our chair. And this is not the only case, okay? Seeing around corners is not the only case. We also want to see through fog, for example. Fog is a complex medium, and there is a way to, okay, with these methods, you can correct for the presence of fog. Or, for example, also multimode fibers. We will see this in the future, in the rest of the presentation, but they're also a complex medium. Why? Because you have a mode mixing inside the fiber, which scrambles the light. So it's very similar at the end, the effect. And when you use a multimode fiber to do endoscopy to see inside your body, then the fiber will get twisted and this destroys the image. So you have to correct for how the fiber is moving inside your body to retrieve the image. Or also if you want to do in vivo imaging. So biological tissues, skin, is also a complex medium. Okay, this all started actually in biological media, and by now, if you want to look at the skull or the brain of a mouse, you have to open a skull, which is not great. While if you use optics smartly, if you correct for this, then you can see inside the mouse brain without killing it, which is great. So, but this is seeing it as a problem. Okay, but this is not what I want to focus on today. What I want to focus is to use it as a resource. Okay, and for this, we have to understand a bit better what happens inside the medium, so how this scattering happens. And we consider a laser for this that gets into the medium. And then what if we measure the light at one point, we can see that each the rays comes as a vector. And upon propagation, this vector rotates, okay? You change the phase of the vector, and then different rays that propagate inside the medium have different phases, and what we end up with is an interference effect, and if we're really close to the center, then we get destructive interference, while if we are far from the center in another point, then we can get constructive interference. So the result is that you get a very complex interference pattern with some points that are very strong in intensity and some points which are very weak. And this is the pattern that we use. Okay, this is the randomness that we get used. And we already go to, okay, one other implication of this scattering, which is the dependence of wavelength, which will bring us to the first application. So different wavelength will have different pattern. Okay, this is very wavelength specific, strongly wavelength specific actually. So what we can do is to use this pattern as an optical fingerprint to understand what was the initial wavelength. Which brings us to the first tool, okay? Now we have this random medium slab of sunscreen that you're using as a spectrometer. Okay, and what you do is that you measure the speckle pattern for different frequencies. Now I consider every nanometers, but we can do this. It will change for a much shorter length scale, wavelength scale. And then you get an unknown wavelength. Okay, if you start from an unknown wavelength, here I show the simplest algorithm, but what we want to do is that we want to check this wavelength is related to a speckled pattern, and then what we want to check is that this speckled pattern, how similar it is to the others. So we study the correlation, which just tells you, are they the same image or not? And if it's not, you have 0 correlation. And when you get the same image, you got 1 correlation, okay? And what this tell you, okay, that the 2 images are the same. And if you do this very finely, what you get at the end is the spectrum of the input light, which in this case was a single frequency monochromatic wave at 770 nanometers. Well, we will come back to the spectrometer afterwards, but now we go immediately to the next application, okay? Again, same, no, sorry. There are different possibilities to achieve this. For example, with a multimode fiber, okay, with a very long multimode fiber, or for example, in an integrated chip. So you make holes in an integrated chip, and this is also a complex medium. It creates the randomness, then generate the pattern, which you see it's the arch on top. And from this, you can understand what wavelength you have, or with a frosted glass, which is more similar to the sunscreen. And what they all have in common is that they have a long path due to scattering, an increased resolution because of this long path. So you can compress it in a very short space and still get a very high resolution. And then you have non-moving parts, and it's a broadband spectrometer. Great. This brings me to the actually next possibility to use as a tool, which is the second harmonic generation. And I start from the beginning. What is second harmonic generation? So you start from a crystal, and some crystals are able to change the color of light. So you start from omega, an infrared light, for example, and you generate something at double the frequency. This is called second harmonic generation. It's what you get from what you get, for example, from your laser pointers, okay? And this is used in general to obtain range of wavelength would be difficult to achieve with lasers. And then the other possibility is to do SPDC, okay? So you down convert photon, it's the other process. So you have half the frequency, and this is used to generate entangled photon and to do quantum optics. And again, I guess we will listen about this later. But how second harmonic work? So second harmonic, we start from this pump, and then what we have is that we start to generate the second harmonic inside the medium, so the signal builds up. But the problem is similar to the one before. So the phase will change, and when you have different phasors, then they go to the destructive interference. And this destructive interference does not allow to get a very strong signal. So what we need to do is to give a condition between the fundamental and the second harmonic, which is called phase matching condition. So we want that the fundamental and the second harmonic propagates inside the medium with the same phase. And this is a strict condition that only works for a certain frequency, for a very specific polarization, for a very specific orientation of the cube, and for a very specific temperature. But this can be extremely efficient, okay? It increases when they're all in phase, it increases quadratically the intensity of the second harmonic with the thickness of the medium. And if your medium does not allow this, what you can do is that you force it, okay? You go there and you turn the medium every coherence length such that you still have a strong second harmonic that increases quadratically with the length. So you get something very efficient, but there is expensive fabrication if you do polling in particular and strict phase matching condition. Okay, this has to be very precise, and it's not broadband. It only works for a very specific narrow band. So what we propose instead, and this is done at TTH, is to take a crystal, divide it into the small cubes that we saw at the beginning, and to just put it randomly around. And what you result with is at the end something, it's a speckled pattern. Okay, so it's again this complex interference pattern, but there will always be a path inside the medium that is highly efficient in second harmonic. So you lose a bit of efficiency because of the randomness. So it doesn't scale anymore quadratically with the length, with the thickness of the material, but only linearly. But what you achieve is something that is bottom-up fabrication. Okay, it's very easy to achieve. You just spray it on your sample, And then you have a very relaxed phase condition. It always works, okay? You go in the lab, you shine any frequency, it works. You are at any temperature, it works. And it allows for broadband second harmonic. Cool. So part of our group works on the physical analysis of this system. But this is what I care about the most, which is a unique platform to study second harmonic and multiple scattering. From the physics point of view, this is very interesting. So there is a physics part of the work, which means that we study different materials, lithium niobate, for example, slabs of lithium niobate, or even these microspheres of barium titanate. The microspheres have resonances inside, so you can enhance the second harmonic generation in these structures. And in particular, for like part of my work was to employ some correlation inside the speckles to enhance the second harmonic and just compress this big, so we don't show the whole speckle pattern, but it can be very large, and I just compress it in few speckles, and all the intensity goes to few speckles to increase the intensity in single spots. But we also use it for applications, and some application is, for example, all optical logic gates. So with the fact that you have the second harmonic, you have two fields that interact, and you have the product of the two fields. This allows for some interesting logic to happen, or we can use it for machine learning. And this I will talk at the end of the presentation, so I will come back to this. And I go very fast to the next topic, which is light focusing. Okay, and for this, we need to add another tool to the game. Okay, complex media are not enough. As we said to the beginning, we want organized disorder, and spatial light modulator helps for this organized disorder. And these are liquid crystal based devices. Okay, you have some pixels, and each pixel corresponds to a liquid crystal layer, and it's similar to, for example, it's used here in the projector to see the light. It's used in liquid crystal displays. But what is the principle? I will go very fast on this, but the idea is that you take the liquid crystal, and it has two properties. One is that when light propagates inside the crystal, it takes different time. It takes different time for different orientation of the crystal. Okay, and this changes, add the retardance to the light, so it changes the phase locally of the light. This is called birefringence. This is just for let's say visual purposes, but this is related to birefringence. And then it has another property, which is the fact that the liquid crystal aligns to an external field. Okay, so with the external field, you can change the orientation of this particle, and with that, you can tune the local phase of the particles. And you can do this for each of the pixels. So what you get is that for each point, you can control the wavefront of light. Okay, this gives a lot of degrees of freedom. You have millions of degrees of freedom that you can play with light. And combined with the complex medium, this allows us to define what is called a transmission matrix. Okay, follow me on this. We have some pixels on the SLM. This will be our input field, and our input modes are the pixels of the SLM. So we have the first pixel, which propagates inside the medium, and then we use a camera to measure the output light. Then we go to the next input, and what we do is that each time we take the output field, and this builds up the relation between what is the input and what is the output. So with this, we can fully characterize the transmission inside the material, which again, it's random but deterministic. So the same light will always lead to the same output. This allows us to generate the transmission matrix, which connects the two fields. And we can use this for focusing and imaging through a complex medium. So let's consider here we have an input field in blue, the SLM, the complex medium, and the output field. Okay, so what we get is that with the SLM, we can invert the matrix. We can write in the SLM the inverse of the complex medium matrix. And with this, it's like the complex medium is not even there, okay? We eliminate the complex medium, and then we have the input field, which is repeated, and you can focus it down, okay? This is why we see a focus in this case. And this brings us back to the first problem. How can we see an image that was before? We do the same trick. So we invert the complex medium transmission matrix, and this allows us to reconstruct the image at the output. And in this case, it is used to achieve a high NA lens. This is the tool that we add here, the high NA lens with the complex medium. Because the complex medium has so many angles due to the scattering that you can focus it down light stronger than with the input lens that you would have here. Okay, so the same device can be used also for high NA focusing. So I will go to the next to the next tool. Okay, it's really like this Swiss knife tool of things that you can do with the same device. And the next is the reconfigurable linear port. So what you have is the input field that goes through the SLM, through the complex medium, and then we consider what I call projection. What it means is that we just consider 3 speckles. Okay, and the trick is the same. So with the SLM, we invert the complex medium and the projection, and we just add the values that we want. So we generate 3 outputs, and of these 3 outputs, we know how much of the input is in there. So we control all the coefficients. And then we add a second input field, and we do the same trick. And we add a third input field, and we can do the same trick. This allows us to create at the end a connection between the input, the 3 input fields, and the 3 outputs. And this is a linear port that we can fully control. Okay, it's a reconfigurable and universal linear port. This can be non-unitary. You can choose as you want the values. So this can be useful to generate so it's easy to scale it up. Okay, the SLM can be made as large as, we can make larger and larger, and the degrees of freedom in the complex medium are basically infinite for what we can control. So we can scale it up to a lot of degrees, or a lot of inputs. Okay, this is a case of 16 by 16 transmission matrix, but you can, linear port, but we can get something even bigger. And we can compare this, for example, to integrated optics. In integrated optics, what you have is that the number of components scale quadratically with the number of inputs. So you have a lot of components, and this creates a lot of, so it's hard to make it bigger. It's hard to scale it up. The system becomes more complex, more bigger, and all of these components are interdependent. So it's difficult to scale it up. But of course, the difference there is the trick is that one is quite slow, while the other one is incredibly fast. So there are trade-offs. But what I want to say is that for certain applications, this could be a possibility when you need maybe slow but very large transformations. Great. So we go now after this plethora of applications. So we can see that this complex media can be used for a spectrometer, for second harmonic generation, for a nonlinear spectrometer, for a high NA lens, and for the reconfigurable linear port, all of this in the same medium with SLM. Now we look at some application, and one is quantum computing. And quantum computing, what we do for quantum computing is the following. So we have an SPD source outside. Okay, we said this before. We generate 2 entangled photons, and then we have a detection part. The detection part is just telling you, okay, I look at 2 different positions and 2 different polarizations. And what the complex medium is doing is to generate a programmable linear port. So you control you take your input state and you control the transformation to generate the output state. And the results of this, in this case, the complex medium is the multimode fiber, and we have the SLM as input. And what you can achieve is different transformations. I can just make maybe the example of maybe the easiest to understand is the last one, when you would expect that the G2 goes down to 0, but if you apply a transformation, then you can make it positive. And you can also scale this up. Okay, so if you have more outputs, if you use a SPAD camera at the output, you can get a lot of output fields and control a lot of output field. And the group that is doing this in Paris of Sylvain Gigan, at the end is limited also on the input only from the setup that they have. There is a single SPD source, but nothing stopped to have bigger inputs. So I will not talk more about this because it's not my expertise, but I want to talk more about photonic machine learning. And for this, let me see how much time I have. Great, enough. So then I will drink. Can you hear me if I speak without the microphone? Great, then I will. So the next thing I want to talk is about classification, machine learning, okay? And I want to give just a flavor of what it is and what the problem is. And we start from a data set with two inputs, okay? And what we ask ourselves is, if I take a point there, is it red or blue? And for you, we are great machine learning machines. And for us, it's super straightforward to say it will be red. But for the computer, it's a little bit more difficult. So you have to pose a condition. And this condition is a linear condition, it's the linear superposition of X and Y. And in this case, it's quite easy also for the computer to understand. You just draw a line, and then you can say if it's red or blue. And this data set means that it's linearly separable. But if we go to a different data set, which again for us is super easy, for the computer already becomes a bit more difficult. So is this red or blue? Clearly for us it's blue, but the truth is we cannot write any of these conditions. It doesn't matter how many lines we draw, we can never realize a circle, okay? You need an infinite amount of lines to realize a circle. So this is not linearly separable, and it's hard to learn for a computer. So what we do at the end is to use a neural network, it's called. In this case, it's a very simple one. Well, what it does is to remap the input data set in something that is linearly separable. Okay, so if you can do this remapping, you know that if you ask where is this point blue or red, the only thing that the neural network is doing is to put it up or down. So it's easy to understand. It's red for the computer. Okay. So this is what we want to achieve with classification, and we can make it larger. Okay, so we take a larger image. Here it's the difference between a 0 and a 1. And we have already 1,000 inputs. Okay, so this scales up quite rapidly. And the truth is that this is slow to train. It's already a lot of transformation that you need to train to understand simply a 0 or a 1, to remap into this very simple 0-1 problem. So what we can do, and on this, you don't have to trust me about math, is to use random weights. So there is a mathematical theorem that says that multiplying by a random matrix preserves the keys information. In this case, it can tell you if it's a 0 or a 1. Okay, and this can be used for even massively reduction of dimension. You can still keep this key information, and then the only thing that remains to train is the last part, which is quite easy and fast to train. Okay, the problem is that this is great. Okay, this already simplifies the problem a lot, but now we already go to a more difficult problem. Okay, and since we're in Padova, we want to understand your very good machine learning machines. I'm sure that you will immediately realize what the two images are, but one is the Basilica of Sant'Antonio, and the other is the spritz. Very easy for us to understand, very hard for the machine. So if we do with the random weights, we can massively reduce this, and then we don't see anything anymore. But for the machine, this is the same. Okay, it looks the same. It's the same image. So we can easily then, well, relatively easily understand if it's a basilica or a spritz. The problem now is that this requires a lot of operation. Okay, this 10 to the 10 operation, you go to the 10 to the 6 system, you go down with matrix multiplication to 10 to the 4. And just to understand, these I could not compute with MATLAB. Okay, I tried, and then MATLAB say, this matrix is too big, 75 gigabytes. There's no way your computer explodes. Okay, so I had to do IMRI size first. What can we do then? So what we can do, I first explain again in matrix, okay? We have the input matrix, then we have this transmission matrix. Okay, already already set it up. We can generate the same system with optics. And follow me with this, we have an SLM, which can encode very large images, okay? And then we have a transmission matrix, which connects to a set of output fields, which are the speckled patterns. And this transmission matrix is the random projection that you need to compress the data, okay? And this, we can do it as, it's basically a physical memory. It stores 10 to the 10 or even larger transformations, and it does it at the speed of light, okay? You do one pass, and you already have your compression. And this is actually, right, the last part, so the last training part, you do it on the computer. And this is done already on from a startup based in Paris. So this is the work that was done in Paris. But now, so this is great. This is an awesome result. But now I want to discuss what are the limits of this. Because this sounds awesome, this sounds magic. There are some limits. And the limits is that you cannot compress this infinitely, of course. And to understand, we have an example with the liver disease dataset that wants to understand if an image gives an healthy liver or which kind of problem does the liver have. And when you compress it too much, then you have the data start to bunch. And then you don't manage anymore to separate them, okay? You cannot learn this anymore. But what you can do then to separate them is to use nonlinearity. And this, you can imagine, goes back to the same idea that is, okay, now we add a strong nonlinearity. These allow us to separate the points such that we can learn them again. Okay, we don't need to control these weights. These can be random weights, okay, due to the random projections. And this can be done optically, okay, and at the end, this is what we show. I hope the paper will come out soon. It's accepted in Natural Computational Science. And what we have is that we goes through the complex medium. The complex medium arbitrarily connects 2 points that will generate second harmonic. And the second harmonic will be randomly mapped to the output. So these exactly match one-to-one to this neural photonic system. And we show, okay, that if we show different data sets, then we always have a degree of, we increase in performance compared to only the linear case. So with this, I would like to conclude, to remember again what we saw today. So the idea is, what is a complex medium? It's just a bunch of particles that are randomly oriented in a disordered fashion. And this can be a problem, okay? It's the reason why we cannot see through the fog, we cannot see through the clouds, we cannot see in a white room. But it also can be used as a resource. It can be used as a spectrometer, thanks to the wavelength dependence. It can be used to generate second harmonic efficiently at broadband. We can use it to generate a high NA lens, and also as a reconfigurable linear port. And we apply these ideas to quantum computing, and finally to photonic machine learning. So this is the overall structure. And at the end, for me, the take-home message is that when you have something that looks like dirt, if you change your perspective, maybe, you know, you can find a treasure there. And I think this is important to learn. And from this, I thank Rachel Grange, Professor Grange, which is my PI, the PI of the project, Andrea Morandi, which is my colleague. And okay, at the very end, the real reason why I went through all of this is to justify my messy desk. Thank you for your attention.
So thank you so much for your enlightening speech. And if you have any question.
Yes.
I'm curious about the linear transformation. No? If I understand correctly, you're basically with the SLN, you are unwrapping the random.
Yes.
But what happens if you don't put the random media? Can you do the same?
If you don't put the random medium, if you can achieve a linear port without the random medium, this is what you ask. Yes. So there is a subtlety there. The complex medium, thanks to you have a deep structure, and so this, let's say, 3D transformation allows you then to control the light more than a single SLM. A single SLM is at the end is a diagonal transformation, if you consider only the light. So you cannot, for example, at the same time write direct light. So, okay, sorry, I explained myself better. To achieve the same thing, you would need to redirect light and also to change its amplitude, which is possible. You use grating in the SLM and you change the weight of the grating, but you're giving more tasks to the SLM. While the complex medium already generate the different points, and then you could select these points. So it's maybe it's a bit simplistic how I explain it here, but the complex medium add this complexity, and plus it is used because you can you also mix modes. You have more degrees of freedom to explore with the complex medium. It's a very good question. Yes.
I have the feeling that with say disordered second money generation, you can no longer use it as it is as a pointer.
Yeah, true.
But what if you combine the linear modulator after that?
Yes, this is a great point. It's not that straightforward because it's not a linear system anymore. So you have you cannot define the transmission matrix anymore. So I want to go back to, I don't know if I managed to go back there, but I will not try. So it's not linear anymore. You cannot define anymore the transmission matrix. You have a tensor which connects, because each of the pixel of the SLM gets inside, and then you have the product of the two pixels. So it's not anymore linear. You have this tensor, and the problem is that you would need to control the product of the input, which you cannot. So you cannot perfectly control the output. But yes, if I managed to get there, there was a work that showed this already. It doesn't work as well, but it does. Okay, so here, for example, these are foci generated after the second moment. So you can do it with SLM, but not that efficient. Yes. Yeah.
Please comment, in some of these applications, you need to recalibrate or measure the transfer matrix.
Yeah.
Could you comment about the stability of these
Yeah.
measurements?
So I can answer to the stability in the lab. And for my measurements, for a work that I did to control coherence, it was stable for 6 months. So I measured it once, and for 6 months, it always worked. But it's an interference, that's an interferometric measurement at the end. So it depends a lot from the system that you have. So I know that other colleagues had just few weeks of stability. For my system that I had, like very short pillars to keep everything very stable. So the system is designed to be particularly stable, and then it can stay there for many months. So you have to design it carefully. Thank you. Yes.
Quickly.
Yeah.
Okay. You're saying that the degree of freedom all you want, but isn't it that you instead are bound to the Fresnel number?
So sure. The truth is that you have the area of illumination over the wavelength. This is the limit. So you have a limit. It's called communication modes of the system. And you have a hard limit of this, but this can go up to 10 to the 6, 10 to the 8 modes. So it's many modes that you have inside the system. It's not infinite. No, it's a simplification.
And you have the points per function.
What do you mean?
Your optical system. So you are looking after all at these things.
So the points per function is part of we can study the communication modes in the system, and the point spread function is also there. So 10 to the 6 to 10 to the 8 is the modes that you have, considering also the finite wavelength of the.
Okay, ideally separate. Ideally, one is to think of the disorder system, and then you have a cheap objective, or you afford a
Sure.
luxury one,
Sure.
then you have a different perspective.
Sure.
So to combine it in the end
Sure.
is random number. Oh,
Sure.
okay.
Yeah.
Great.
Thanks.
Yeah, just curiosity, about the high NA lenses. How would you like place them in, for example, microscopy? Would they help like overcome the diffraction limits, or I don't know, they stop it?
So it depends what you mean with overcoming the diffraction limit, in the sense that so you can get high NA, you're limited by the system itself. So the size of what it is in the work is that the size of the speckle only depends on the physical property of the material. And this can be, it's usually on the order of the wavelength. Okay, so you're not overcoming the diffraction limit in this sense. So you cannot go smaller than the wavelength, but it's related to the optics that you have. So the fact that even if you have a cheap lens, then the complex medium can help you to have very high angles. Okay, you increase the angles. Of course, you need to have an SLM to achieve this, which is the problem. But if your system already have an SLM, then you can use just a cheap ground glass diffuser to achieve very high NA.
Okay, if there are no more questions, I just have a past curiosity. About the pre-compensation you were commenting at the beginning to see behind the corner. You said, that, if I understood correctly, that this works because there is the deterministic pattern
Yes.
in the complex medium. So I was thinking, if you think it's possible to somehow control, maybe with a feedback loop, in a way to deal with the dynamic, non-deterministic medium.
This is a big problem of the field, okay, of the field that wants to study biological tissues, because at the end, this is studied a lot for biology. And then this will change continuously your medium. The short answer is that no, it's difficult because you have it inside, right? So you don't have access actually to the field there. So the solution are, for example, they use guide star, which means that, for example, in your multimode fiber, at the end, you have a tip, a fluorescent dye, only a small fluorescent dye, which gives you a feedback on how the transmission matrix is changing, and then you can correct on the go. But it's an open question. There's a lot of research to actively feedback loop the transmission matrix on the go.
Thanks. I think we can take 10 minutes break. Thank you again.
Thanks a lot. Thank you. And I hope it can be part of the next photonics call. I hope we convince you to bring it to the next photonic call in Brussels. Not yet, but
Yeah. Okay. Well, let's check in the research agenda.